All right, in today's lesson, we're going to be looking at solving quadratic equations. So for our first problem here, we have the following quadratic we want to solve. There's two ways you can go about solving this. Typically, what you want to do is you want to bring everything to one side. You want to get 0 on the right or left-hand side here. So let's go ahead and do that, giving us the following. We end up getting 4p squared minus 16. Next thing we want to take a look at is, does the following quadratic have a GCF? It does. That's a 4. We'll factor out that 4, giving me 4p squared minus 4. And you'll see inside here we are left with a difference of squares. Again, I can express that as 2 squared. And our difference of square formula says this factors into p minus 2 times p plus 2. So again, we have the product of two expressions, 0. Either the p minus 2 is 0 or the p plus 2 is 0. And solving for these here, you'll see p minus 2 is 0 implies that p is 2. Or p plus 2 is 0 is going to imply that p is minus 2. So the zeros or roots for this quadratic are 2 and negative 2. Solving the next quadratic here, again, we want to solve this equation. So bring everything to one side. Doing so, we get x squared plus 2x minus 15 is 0. Right away, taking a look at this here, you see you have a simple trinomial. Leading coefficient is 1. We're hoping we can solve this using product sum. Doing a quick check here, my product is negative 15. My sum is 2. I need to think of two numbers that multiply to be negative 15 and add to be 2. That's going to be 5 and minus 3. Once you find those two numbers, this will now factor into x plus 5 times x minus 3 is 0. And again, we have two options here. That must mean that either x is negative 5 or x is 3. Let's take a look at some others. So for the next set of questions here, again, this one is a bit different. You'll notice I do have myself a simple trinomial, but if I start to go and find numbers whose product is negative 3 and whose sum is 7, and going through those combinations, you won't be able to find that. And if you do a quick discriminant check on this, you get b squared minus 4ac, and I get my discriminant here is 49 plus 12, ends up being 61. So that my discriminant is greater than 0. I'm going to have two real roots for this equation, but these roots are going to be irrational. So we're going to have to go right to the quadratic equation to solve this. So this is x is negative 7 plus or minus the square root of my discriminant divided by 2 times a. So the roots for this are negative 7 plus or minus the root of 61 over 2. And again, this isn't always the case, but if you do have a quadratic such that its discriminant is a perfect square, there's a good chance you can factor it using the charting methods. However, if it is not a perfect square, this can only be solved using our quadratic equation. All right, let's take a look at the next question. For the next one here, again, the idea here is we're solving this equation, and this equation is set equal to 0. And when something's set equal to 0, you can multiply across by anything you want. So in this case here, I'm going to multiply across by 3. And this will rewrite the equation as 2x squared minus x minus 15 is 0. And now solving this equation is exactly the same as solving this equation. These are not the same quadratic, but they have the same roots. They're going to look different, but they're going to cross the x-axis at the same spot. So we can go ahead and multiply across by 3 here and solve this equation, giving us the same answers. So right away, looking at this here, I'm going to go ahead and calculate my discriminant just to see whether we can actually solve this by factoring. So I have b squared minus 4ac here, and my discriminant ends up being 1 plus 120. Putting that together, we get 121. That is, in fact, a perfect square. So we can go ahead and do charting on this if you want, or you could continue just with the quadratic equation anyways. But I'll go ahead and do charting on this. And you'll see here I get the following two columns work here. The product of these diagonals, when I add them up, I will get a negative 1, which is what I need to get here. So this is going to factor into x minus 3 times 2x plus 5 is 0. And the roots for this are going to be 3 and negative 5 over 2. All right, let's take a look at a couple more examples. So in the next example here, now again, we got to clean this up before we go ahead and decide how we're going to go about factoring this or using the quadratic equation. So I'm going to expand this out. I get x squared minus 4x plus 4. And bringing everything to one side, we get x squared minus 5x minus 6 is 0. And you'll notice here right away we have a simple trinomial, and I need to think of two numbers whose product is -6 and whose sum is -5, and I can see those right away as being -6 and 1. So this will factor into x minus 6. X plus 1 is 0, and the roots here are going to be 6 and -1. On the right hand side here, we're going to go ahead and expand this out. So we're going to get here square the first times second times 2, and square the last. And we're going to go and expand the right hand side again. Here we're going to get 4x squared, and first times second times 2, and square the last. We get 9 this time. So again, now I've expanded everything out. I can go ahead and bring everything to one side, giving me 5x squared minus 18x minus 8 equals 0. Again, when you're looking to solve these equations, you want to take a look at, is there anything I can factor out of this divide across by 5 or 3 or something along those lines? And this doesn't have a common factor here, so we can't go ahead and do that. Let's go ahead and use the discriminant and see what value we get here. If I calculate my discriminant, I get my b squared minus 4ac. So go ahead and calculate this here. I end up getting the discriminant is 44. That is a perfect square. You'll notice that the square root of 44 is 22. So we should be able to factor this using charting. Let's go ahead and do that here. And right away, you'll see this factors into x minus 4 times 5x plus 2 equals 0. And we have two roots here. One is 4, the other is -2/5. All right, let's take a look at a couple more examples. So the next example here, same idea. We want to go ahead and expand this out and simplify. So we're going to go ahead and do that, giving us the following. So expand this all out. Here we get the following. We're going to go ahead and collect like terms. You can see here we have like terms between these two. This gives me 2x squared plus 3x plus 1. And is going to go ahead and equal x squared minus 2x plus 1. Bringing everything to one side and simplifying, we end up getting x squared plus 5x equals 0. You notice here the 1's will cancel off here. Now if I'm going to go ahead and solve the following expression, the first thing I want to do is see, is there a GCF on this? And there is. I can factor out an x, leave me with x plus 5 equals 0. And now the only way we can solve this, either the x equals 0 or the x plus 5 equals 0. Therefore, either x is 0 or x is -5. Take a look at the last example here for this section here. We want to go ahead and solve this. First thing you want to do is there a GCF on this? There is GCF of 3x, leaving me with x minus 6 equals 0. And again, two situations, either 3x equals 0 or x minus 6 equals 0. Which means either x is 0 as one of the roots or x is 6 as the other root. All right, let's take a look at some more examples. So in this example here, we want to go ahead and solve this. So I'm going to first rewrite this with the highest power, followed by the next highest power, followed by our constant term. Go ahead and get rid of that minus sign by multiplying across by -1. So we get 4x squared plus 6x minus 8 equals 0. Divide across by 2, I get 2x squared plus 3x minus 4 equals 0. And if we do a discriminant check on this, we end up getting here 41, which is not a perfect square. It is greater than 0, so we're going to have to use the quadratic equation to solve this. Using our quadratic equation, again, we're using it on this expression here. End up getting x is -3 plus or minus. Don't forget, we've already calculated the discriminant, so we know it's 41. Divided by 2 times 2, and the roots for this are -3 plus or minus the root of 41 over 4. Let's take a look at the next example. This is going to be expanding this out. We get 3x squared minus 9x plus 2x squared minus 4x equals 1. Collecting like terms, we get 5x squared minus 13x minus 1 equals 0. Again, I brought the 1 on the right-hand side to the left-hand side here. Now again, I want to go ahead and factor this. Checking the discriminant, I get b squared minus 4ac. I end up getting d is 169 plus 20 is 189. And I get that is greater than 0, so that's going to give me two real roots. And not a perfect square, so using our quadratic equation, I get x equals negative b, so -13. Plus or minus the square root of 189 divided by 2 times 5. So I get x here is 13 plus or minus the root of 189 over 10. And these are our two answers for these two questions here. Moving on, we have the following. Now we want to go ahead and determine the types of roots that we have using our discriminant here. So we've been using the discriminant quite a lot. So we want to go ahead and first realize that to use the discriminant, you must be in standard form. And there's no need to have a negative sign with your a value. I'm going to multiply across by -1, giving me 3x squared plus 2x minus 1 equals 0. And using our discriminant here, I end up getting b squared minus 4ac. And the discriminant here ends up being 4 plus 12 is 16. That's greater than 0, so this is going to give me two real roots. Two real distinct roots for this example. So in the next example here, we can go ahead and multiply across by 4, giving me 5 minus x squared equals 4x. I'm going to go ahead and bring everything to the right-hand side, giving me x squared plus 4x minus 5. Now I know my a value here is 1, my b value here is 4, and my c value here is -5. Subbing this into my discriminant, I get b squared minus 4ac, and I end up getting here 16 plus 20 is 36. And that is greater than 0, so again, this example here will give me also two real roots. Let's take a look at an application question regarding the discriminant. So this example here, there's two of these here, and what's going on is they give you a quadratic, but you do not know the b value in this example. In this example, we do not know the a value, but what they want you to do is find the value of k such that each of these quadratics has exactly one root. So what we do here is my a value for this question here is 1, my b value is k, that's what I want to find, and my c value is a -4. But what I do know is that the discriminant of this is exactly one real root. So I know my discriminant, d, which is equal to b squared minus 4ac, I know it must equal 0. So I have this relationship here I can use, which means that in this example, I have k squared minus 4 times a times c must equal 0, which implies that k squared plus 16 equals 0. And you notice with this one here, if I go to solve this, this has no solution, right? This here is unfactorable, right? If someone gives you the equation x squared plus 16 equals 0, there are no real numbers that you can square that'll yield a -16 to cancel that positive 16 and bringing that to 0. So for this example here, there is no value of k such that this quadratic will have exactly one root. That is impossible. Let's take a look at the next one here, though. So same strategy, though. So for this one, I know my a value this time is k. My b value is -10. My c value is 2. My discriminant, which is equal to b squared minus 4ac. I set that equal to 0. I get 100 minus 8k. And I end up getting 8k equals 100. K equals 100 over 8, which I can divide by 2. I get 50 over 4. Divided by 2 again, I get 25 over 2. I end up getting 12.5 here. So what that means here is that if I let k be 12.5, then this quadratic will have exactly one root. All right, that concludes today's lesson on solving quadratic equations. Thank you.